Hello everyone, this is Jared back with another video. This time we are doing a two-stage vapor compression refrigeration cycle. This one's kind of a doozy. It's going to be a little long, but if you need to see the values, just wait there and just pause the video, write those down. But besides that, we're going to get right into it. I feel like I say that every time. So, we are starting with state 1, which is going into the compressor. And we know the state 1's values are T1 to be negative 30 degrees Celsius, and it is going in as saturated vapor. X1 equals 1. And so we know H1, if you just go to the tables, this one is once again refrigerant 134. This is just Hg at that pressure, or at that temperature. And you get 229.14. So just slide across the table and pull these values out from the Hg column. Yeah, I'm trying to move through this one quick because this one could have been long, as I'm sure you guys are aware. This problem could be lengthy. And so state 2, we know pressure 2 is equal to 4 bar. And S1 equals S2 because we are assuming isentropic operation of the compressor. And so we, as we have done, I don't know, 100 times before, we solved through the compressor using the perfect isentropic case. So S1 equals S2. And S2, which we're once again trying to find out, if you don't know where it is, you try and find out where it's at. So you go to 4 bar, and you would notice that S2 is greater than Sg, which means it is a superheated refrigerant. And so, since we know that, we can then go to the table. Once again, I think this is A20 or A12E, and you just pull it up at 4 bar. Or no, this is it should be A12. Just A12 because we're not in English units anymore. And you'd get an H value to be 260. Yeah, I forgot we were in English units, but we're not. We are in the better unit set. And so for this cycle, this one's kind of different. You cannot solve through 3 and 4 without having further information. So we are skipping straight to 5. Yeah, you have to do some there are some unknowns that you have to have before you can solve 3 and 4. So moving right along, state 5. Well, we know that pressure 5 is the maximum pressure in the cycle, which is 12 bar. And if I recall correctly, let me check my handy dandy sheet. Yep. X5 is equal to 0, which means we are assuming it comes in as a saturated liquid, all liquid, which means H5 is just equal to HF at the pressure 5, which is 12 bar. So you go to the 12 bar saturated table for 134A, and you will find HF to be equal to 115.76. And state 6, once again, everybody's favorite part. We are going through a valve, and so valve properties, you know H6 is equal to H5. Loses no enthalpy, but loses entropy. Or gains entropy, I guess you could say. But for this problem, we need to find the quality at 6. If you recall, you drop down from 5 into the saturated region at the pressure below it, so at 4 bar. So we have to find X6. And X6 is equal to H6 minus HF over Hg minus HF. That is derived from the, if you were trying to find H6 equation and you had X6, If you maneuver it all around, you'd get the original H equation, knowing quality. But obviously we're looking for X6, and we're doing it at pressure 2, which equals pressure 6, the medium pressure. And we see that X6 is equal to 0.28247. So 0.282, I guess you could say. Yes, and circle that. That's important. I'm glad I did that. Alright, and now moving on. So now that we know, I'm going to give you a diagram here. So we have 6 going in. We have 7 leaving through the bottom, and 9 going out. This is the flash chamber. And so inside of here, those little particles are vapor, by the way. I didn't know how to draw vapor. And the bottom part, obviously liquid. And so you have the vapor going that way through some sort of fan pushing it out. And you have liquid dropping down because it obviously doesn't float. So you have X9 is just all vapor, right? And this is where it gets confusing because we use X's to denote the mass flow rate, like the percentage of mass going one way or the other. But for this one, I'm going to break it down differently because I don't like that we keep interchanging these, because X obviously we all think is quality, and so I'm using them as quality. X's and mine are quality. So X7 is equal to 0 because it's all liquid, and X9 is equal to all 1 or is equal to 1 because it's all vapor. So we're going to solve state 9 first. Just keep that in mind. So X6 is equal to the amount. Okay, let's see what I write here. I don't even remember that. The amount of vapor. Because remember, if you look at the X equation, it's mass of vapor over total mass. So that's the amount of vapor that is in this mixture region. So I am denoting, so Y9 is my, you remember in the 1 minus X thing, where it shows you the percent of mass going one way, I'm going to be using Y9 there instead, just to keep, I know it might be confusing to you, and you might want to do it that way, but I just want to break it up more because I don't want to confuse X's. So then we get our H6 value, which is Hg at P9, which equals P6, because we know it's all vapor at state 9. And you get 252.32. And then we move on to state 7. And now we know state 7 is all liquid. And Y7, so it's the rest of the mass, which we know is all liquid. So it is 1 minus Y9 equals Y7. But obviously we're just going to be using Y9s in this. That's a Y9, not an X9. We're going to be using Y9s, but I just wanted to show you that is the rest of the mass. If you wrote it like that, it works out. It checks out. So, and like I said, this is percentage of mass. This isn't quality. Quality is the X's in my world. And see, I think, I changed it here. I don't really know what to call it. I guess it may be direction of mass, like where it went, right? So I guess you could say percent of mass going one way or the other. Because if you think about it at H6, anyway, H7 is equal to HF at P7. what I was going to say is at the valve, you know H6, or X6, rather, is the mass, the total of the vapor, right? It's the vapor over total mass. And so you know that all the vapor went one way, right? So you know that 9 is equal to 6. I just like to know. I just don't like things being confusing, and maybe I'm confusing you right now, and if I am, I apologize. But this is just how I think of it, and you don't have to do that. If you know, like, let's put it this way: if you know that all of the liquid went to 7 and all of the vapor went to 9, then you don't need to use the y's. You can if you have it in your head that you know this, you'll be fine. You can use the x's, but like I said, sometimes it confuses me, so I like to have something else to remind me. All right, and now we're doing state 3. This is another little heat exchanger, the intermediate heat exchanger before the second compressor. So we have 2 going in, 9 going in, and 3 leaving. And so we have to, I think I make a mistake here, but I will explain it. But so it's an energy balance is what we're going to do around this heat exchanger. And so we have 0 equals m dot. I think the m dots aren't necessary here. That's what I shouldn't have the m dots. It should just be 1 minus y9, which is what I'm using. Remember, that is my percent of mass, I guess you could say, going that way. Yeah, just the m dots aren't necessary because it's implied already. It's basically like implied. We don't need that. So just think of it as like the m's aren't there. Because we're just talking about direction of mass and energy. So we don't actually need mass flow rate at the moment. So we would have 1 minus y9 times h2 plus y9 times h9 equal to h3. And yeah, I think about it right here, and I just will decide to leave it. But like I said, I know I've said this in previous videos, I like to write everything out just so I don't think, and then I look at it to make sure I didn't forget anything. And in this case, I wrote too much. You don't need those, but like I said, I feel like it's better to write everything than to write not enough. Just my philosophy. So basically, I'm the opposite of Hakuna Matata. I have all worries whenever I do problems like this. And so we have Qn. So we're solving for mass flow rate, which because we need to have to solve later in the problem. So we're solving for mass flow rate here. And so we are given that Qn is equal to 10 tons, and we need to change this to kilojoules per minute so we can get our answer, our mass flow rate, in terms of something per minute, like kilograms per minute. And so we know that Qn is equal to H1 minus H8 times mass flow rate. And we know that 10 tons times 211 is equal to kilojoules per minute. And so if you do this conversion and you divide over H1 minus H8, you will get 12.624 pounds per minute. But I think we should probably change, I think I end up changing that to per second. In a second. In a second. How funny am I? And so what I'm saying here is that we're solving this energy balance now. And like I said, you don't even need the mass flow rate, I think. I think you just solve for, I think you'll end up just getting the same thing anyway if you do it with, yeah, see, you remove the mass there. Right? I think I've discovered it here, is that like, you don't really need that. And so anyway, basically what we're saying is that we're solving for H3 through the energy balance. And so H3 is equal to 1. This I got rid of the mass flow rates here. See, 1 minus Y9 times H2 plus Y9 times H9. See, you just got to wait a little bit and maybe it becomes more clear. And you end up getting something to the effect of 258.3. This is in BTUs per pound, I guess it would be. And then S3. You would look this up in the table with your H3 value, and you would find out, once again, is your H3 bigger than Hg? If so, it's superheated, which in this case it is superheated. And you'd interpolate at pressures for that S value. And now we're moving on to state 4. And with state 4, I'm doing a calculation really fast. Okay, yeah, it works out. Anyway, making sure on the fly here. And so state 4, we are solving through the compressor again. And the reason why we had defined S3 was because we have to solve through the compressor as we do on the other ones, which is through isentropic relationship. And so we're not going to spend a lot of time with this. You go through the table, you find out whether S is greater than Sg. I guess we are going to spend time on this. But you do it at the maximum pressure this time, which is 12 bar. And it is superheated. And so H4 is equal to 281.726. Once you look it up in the table, that is. And now we're moving on to the answers part of the problem. I think that's what we're doing. Yeah, solutions. Okay. So, part A of this problem is asking for the work of both compressors separately. So, we are going to solve them both here in kilowatts. So, the first compressor, that one's pretty easy. We already have the mass flow rate at the first compressor, which is what we solved for earlier through the condenser, I think. Through the heat in, whichever one is on the very bottom. I'm not sure. I can't remember which one it is, but I think it's the condenser. Or no, it's the evaporator. Got it, I think. And so, you solve it. So right here we have the mass flow rate in kilograms per minute. We must turn it to seconds to get kilowatts in the end, because a kilojoule per second is a kilowatt. And we have these in kilojoules per kilogram. So had to make sure the units worked out to get them in kilowatts. And so right here, if you multiply all that together, I'm just setting it up right now. We're gonna write this out later whenever we solve for the next part, because work compressor 2 is actually not as easy to solve for, because we do not have mass flow rate of 3, because the mass flow rate of 3 is different than the mass flow rate of the first one. Because remember, mass flow rate of 3 is 100%. They've all joined back together at the heat exchanger. Mass flow rate of 1 is just whatever percent went down through the flash chamber. So we have to find mass flow rate of 3. And so what you will, if you think about it, the mass flow rate of 3 times 1 minus y9 is equal to our mass or whatever our mass flow rate of 1. And what that basically what that is saying is so say that mass flow rate of 3 is 100%, right? This is just me being an example. Mass flow rate of 3 is 100%. Mass flow rate of 1 is some other percent. Multiplying mass flow rate of 3 by, let's say, 20%, right? Or 0.2 gets you the mass flow rate of 1, which is the mass flow rate dropping down. And I wrote it as a mass balance. I'm not sure that's what it is. I think it's just it's percentages going in directions. And so that's what we're saying is that if you multiply 1 by 0.1, right, you will show that means the mass flow rate of 1 is whatever that turns out to be. Like you know what I mean? It is a percentage of mass going one way or the other. And so we're solving for mass flow rate of 3. And so what I was saying is that if you multiply our mass flow rate or if you divide over 1 minus y9, which is the percentage of mass going towards the right, like after the flash chamber, or no, dropping down. It's dropping down through the flash chamber, pardon me, which is what our mass flow rate is from the 1 part, like the mass flow rate of 1 going down to the bottom part of the cycle. If you divide our mass flow rate by that number, 1 minus y9, you get our mass flow rate of 3. So basically what it's saying is that our mass flow rate of 3 is equal to our mass flow rate of 1 divided by the flow that went down there with it. Because if you divide by a decimal, it got higher, which means mass flow rate of 3 should be the total mass, which means we have 0.293 kilograms a second total is our total mass flow rate, which is bigger than the one at the bottom, as you see. Which means that makes sense. If you got a smaller mass flow rate at mass 3, you know something's wrong. And so since we know all of this, this right here is just solving that first equation, the work compressor 1. You just put the mass flow rate you just solved for in the work of the compressor equations, which is H2 minus H1, using the first mass flow rate, m dot 1, and then m dot 3 times H4 minus H3. Sorry, it's hard to explain like in a coherent way, I guess. It's also late. Pardon me. So, for this last part, it's the COP of the cycle. And you notice I wrote QN over work cycle, not QN over work compressor, because we have to include both of them. And so our QN, which was given in this problem, but it was given in units that, aren't very helpful when it comes to work of the cycle. They have to be in units that cancel each other. And so this right here is the equation you would use. And if you do this, if you put in all your H values and your M dots, all that fun stuff, you will get a COP to be equal to 2.61. And I think that is the end of the problem. If you have any more questions, you can send them to my email. But if I'm not the TA, ask your professor. And that's it. Thank you for watching.